In this video, I will write a proof for the product rule for derivatives. The statement is summarized by this equation here. The derivative of a product of two functions is the derivative of the first times the second plus the first times the derivative of the second. The formal statement of the theorem is a bit longer. I first have to introduce my notation. A is a real number, f and g are functions defined at and near a, h is the product of f and g. Then the theorem says, if f and g are differentiable at a, then the product is also differentiable at a, and we get the equation. The if-then part matters. If f and g are not differentiable at a, then the equation is not true, and the derivative of the product may still exist and have any value. I went a bit fast through this. I explained it a bit more slowly in a previous video, which I will link in the description. Now it is time to write a proof. First, I write a definition of derivative. There is only one thing I can do next. Use the definition of h, both for h of x and for h of a. Now I need to stop to think. I want to relate this expression to the derivatives of f and g. If the two appearances of g were the same, I could factor them out and I would be left with the derivative of f. But they are not the same. Similarly, if the two appearances of f were the same, I could factor them out and I could be left with the derivative of g. But they are not the same either. I am going to add and subtract some terms so that I can factor things out. First, I copy the exact same expression. And then I add and subtract the same term. This is certainly legal, because I have effectively added 0. But look how it helps me. In the first two terms, I can factor g of x. And after factoring it, I am left with the derivative of f. In the last two terms, I can factor f of a. And after factoring it, I am left with the derivative of g. Let's regroup the terms this way to make it more clear. Now, I recognize some of these pieces individually, so I will try to use the limit laws and write this limit as sum and product of limits of each of the four pieces. Wait. For the purpose of the limit, the variable is x, not a. F of a is not a function of x. It is just a multiplying factor. It acts like a constant. In order to do this, since I am using the limit laws, I need all the individual limits to exist, but I am going to justify that now. The first piece is the derivative of f at a. But I can only say this because we assumed f was differentiable at a. Similarly, the last piece is the derivative of g at a. Again, because we assumed g was differentiable at a. What about this limit? It is tempting to write that it is g of a. But can we say that? This limit being g of a is exactly the definition of continuity. Do we know whether g is continuous at a? Yes, we know. We are assuming g is differentiable at a. Differentiability implies continuity, therefore g is continuous at a. And so, I have proven that h prime of a equals f prime of a times g of a plus f of a times g prime of a. And that completes the proof. Two important notes. It was essential to assume that f and g were differentiable at a. Otherwise, I could not have been able to use the limit laws in this step. And also, I had to explain how I know that g is continuous at a.